Good afternoon. Today we're going to be discussing exponential functions, continuing our discussion of functions that we started half a semester ago. We've looked at quadratic functions, piecewise functions, polynomial functions with their zeros, inverse functions. I think I'm missing some other functions. Today we're going to look at exponential functions. But before I define what we mean by exponential, I want to review some rules of exponents. As a general rule, I don't specify when we're doing foundations and when we're doing algebra, but today it'll be pretty obvious when we're doing the foundations, when we switch over to the college algebra material. And first up here is some rules about exponents. And the first rule I'm stating is anything to the 0 power is 1. I'm making a huge assumption. We've seen exponents all semester. So the little number up here is an exponent. This A is called a base. We have the rule, anything to the 0 power is 1. It doesn't matter what the base is. Okay? Anything to the 0 power is 1. That's what that first rule says. And
so 6 to the 0 power would be 1?
6 to the 0 power would be 1. That's right. Did y'all hear that?
So
what about problem number 1 here? Is there anything I'm going to need to type in? No, just 11 to the 0 power is 1.
I can pass this.
Okay.
Almost do the same thing.
See. No, this one's a trick. I wanted to do, this is still number 1.
Negative 1?
Notice, is the negative also being raised to the 0 power?
Yes.
The whole set of parentheses is being raised to the 0 power. So this negative 43 all raised to the 0 power, that too is a 1.
But it's not negative.
It's not negative.
Okay.
And I wanted to mention with a calculator, a lot of times students forget if they see parentheses like that, they don't enter the parentheses. If I put this in, the way I enter an exponent other than a square is to use this little carrot top symbol there. I've already checked this and it told me it was right. But if I punch it in like this, look at what it's going to do. It gives me negative 1, which is wrong. But what's wrong here? I entered it wrong. If you enter it without the parentheses, the negative isn't being raised to the 0 power.
So
What's immediately to the left is 0. The parentheses, everything in the parentheses is being raised to the 0 power. If you wanted to do this problem with parentheses, with a calculator, make sure you enter it in the parentheses the way it's written here. Okay?
So the rule would be if there's anything in the parentheses, even if it's negative, it's always positive?
Positive 1. Anything to the 0 power is defined to be a positive 1. Sometimes students don't believe it unless they see it on a calculator.
I have the same one.
Oh, yeah, you do. Oh, it looks just like this one, doesn't it?
So both of those for question 1? Both of those for like a question?
Yes, I did question 1 and I clicked similar question. If I click similar question again, what am I going to put in here for the answer? 1. All I've done at this point is problem number 1. But to do problem 2, we need a couple of more rules. The first rule that I stated is the definition of a 0 exponent. Now I'm going to state the definition of a negative exponent. A to the negative n power. So a number to a negative power does not equal a negative number. A negative exponent means the fraction 1 over. For example, if you had to figure out 3 to the negative 2 power, the answer is not negative 9. Do y'all see what I'm doing with the colors? This red negative on the exponent is the same thing as a 1 over.
So what if 3, 2?
So 1 over 3.
Negative 6. Well, we would get rid of the negative?
That gets rid of the negative.
Right.
Okay? The red negative means the red 1 over. And now y'all know what 3 to the second power is. What's 3 squared? 9. So 3 to the negative 2 is not negative 9. It's 1 over 9. And that's just an example.
That's the answer they'll expect.
Having seen that, could you tell me what 4 to the negative 2 would be? Okay, just a plain 16 or 1 over 16, right. Now, so this green rule we use for a number to a power, a negative power. There's another rule about negative exponents that I'm writing right here, and it's how you'll raise a fraction to a negative power. If you have a fraction raised to a negative power, instead of going 1 over, all you have to do is flip the fraction. A over b to the negative n. If you had a fraction to a negative power, that's the same thing as b over a, so flip the fraction to the positive power. Yes. So, suppose we had this. 5 over 6 to the negative 2 power. It's not your answer will not be negative.
6 over 5 to the second.
Exactly. Did y'all hear that? That's what this second rule is right here. To rewrite, if you have a fraction to a negative power, flip the fraction and change the exponent to positive. So it would be 6 over 5 to the, can y'all see my positive 2 exponent there? Now don't say 12 over 10. What's that going to be? 36 over 25. Now, problems 2 through 9 are going to use those 2 green rules there. The negative exponents. You'll either have a number to a negative power or a fraction to a negative power. And you might even be using this rule here in reverse. But let's get over here and see it first. Problem 2. Okay. Here's problem 2. It says 1/5 to the negative 2 power. Did y'all hear that? Very good. Let me see. All ahead. Let me move over here.
25.
Okay. So it's a fraction to a negative power. So using this rule right here, flip the 5 over 1. Flip the 1 over 5. And you get 5 over 1. But do I need to really write it as 5 over 1? You could just write it as 5 squared, which is 25. So 1/5 to the negative 2 power is 25. Might not be what you would think if you didn't know how to work with negative exponents. Oh, this is a good one. Number 3. 2/5 to the negative 4 power. So I'm going to write it without the negative exponent. I'll lose that red minus sign just by flipping the fraction. So I'll write it as 5 over 2. Oh, what's that? Let me see. Oh, yeah, okay. To the 4th. Say it again. I agree with the 16. 2 times 2 times 2 times 2, the bottom. If you multiplied out 4 2's, you'd get 16.
5 to the 4th is 625.
625. 5 times 5 times 5 times 5, that's 25 times 25, so 625.
I was way off.
Yeah, I my calculators.
I did too. I'm trying to do it in my
Yeah.
head. That's why I'm off.
Oh. Let's see. So if you did something like 5 raised to the 4th, 625. Okay, so you can use a calculator for stuff like that. Oh wait, I didn't write in the answer, did I? It's 625 over, what did y'all say, 16? Okay, problem number 4. Oh wow, it says rewrite using a positive exponent. We have a to the negative 4 power and we want to write that with a positive exponent. We don't want that negative in front of that 4.
So it would be 1 over a, whatever it is.
Y'all hear that? It's this rule right here. A to the negative n. If you just have a number, if it's a fraction to a negative power, you flip it. But if it's just a number, not a fraction, then that negative means 1 over. So it would just be a 1 over a to the 4th.
I've done it before. I did it last semester.
Okay.
Yes, I did. I'm remembering it from last semester.
Oh, okay. So let me see, I'm going to type 1 over a raised to the 4th power. Any questions? Y'all caught up with me? Okay. Now here's something interesting. It says write it using a negative exponent. Usually what we want to do is take a negative exponent and write it with a positive exponent. But there are times when we're going the other way. Here we have a 1 over 7 to the 5th. And we're going to write it with a negative exponent. See, basically we're using this rule going in reverse. If you want to get rid of that 1 over, you make the exponent negative. There, if someone says, say something from that you learned in algebra today, one thing you could say to get rid of a 1 over, make the exponent negative. And that's what we're doing here.
So then would it be 7 over
No, this is
7 to the negative 5. Okay. See, 7 to the negative 5 is the same thing as 1 over 7 to the 5th. So I'll type in 7, hit my exponent key, negative 5. Okay. Problem number 6. Is this one hard or not that hard? Okay, it's 1 over p to the 6th And we're going to write it with a negative exponent.
You're threatening to smack me.
Are y'all caught up with me?
No.
Oh, okay. So, on problem 5.
So P negative 6.
Oh, wait. So y'all up to number... Are y'all ready to do this one? Let me... Okay. To get rid of a 1 over, you make the exponent negative. So this 1 over p to the 6th is a p to the negative 6th. I'm not sure if it's obvious what I'm trying to show with the colors. But this red 1 over is the same thing as that red negative. That's what I'm trying to show with these colors. Just like up here when I stated the rule, that's almost at the point where you can't see it. Okay? Any questions? Oh, wait, I didn't type it in. Okay. P will be raised to the negative 6th. Number 7. Right? Oh. Before we do number 7, I need to state some new rules. Not new. Here's some rules that we're going to use for those. And it's rules that, you know what? I'm going to do what I accuse my brother of doing all the time, wasting paper. But it's a rule that we saw on when we were solving equations with square roots in them. We've x.
So this is the rule?
Yeah, this is a rule. And I wonder if y'all remember this. A 1/2 exponent is the same thing as a square root. A 1/3 exponent is a cube root. I think that maybe your first test had a problem that looked terrible. 2x minus 5 to the 1/3 minus 3x plus 7 to the 1/3 equals 0. But it turned out to be real easy. A 1/3 exponent is a cube root. A 1/4 exponent is a 4th root. And so forth. In general, what we can write is this. X to the 1 over n power. 1 over 5, 1 over 6, 1 over 7. If you have an exponent that's a fraction, that bottom number is the root. So x to the 1 over n is the nth root of x. Problem number 7, which I pulled up a moment ago and started to do, says, rewrite without rational exponents. Remember, in algebra, rational is just another word for fractional. So we're going to rewrite this without a fractional exponent. Then it says simplify if possible. There's not much you can do to simplify. Let me write this down. This is an x
Square root 5.
to the 1 over 5 power. Okay. A 1/5 exponent if it's a 1/2 exponent, that's a square root. You don't really write the little square there, but you assume it's there. A 1/3 exponent, cube root. A 1/4 exponent, 4th root. The way you would read this, in place of this little 1/5 exponent, you write the little funny symbol which is called a radical symbol, and put a 5 right there. And how do you read it? You read it as fifth root of x. The little red symbol, you read that as root, like cube or third root of x. Fourth root of x. Nth root of x. So, that's it. X to the 1/5. That's why I stopped right here after x to the 1/4. I saw what number 7 was a moment ago. So I'm going to, well, you type that in, use this symbol right here. Put a 5 for the root, and an x right there. Any questions? Are y'all caught up with me? Oh, Number 8 says 64 to the 1/3 power. Let's see. 64 to the 1/3. 1/3 is that little cube root symbol. Okay. So, hey, just say cube and root. Don't say square root. Just the cube, the little 3. You start with that. Cube, just say root of 64. If you say square root, then you're assuming it's one of those things where there's not a number right there. If you don't see a number there, you assume it's a 2. That's why you read it as square root. You read the little number, then you read the symbol as root. So cube root of 64. Don't say 8. 8 times, say
That's what I was.
that's the square root of 64. What about the cube root? Let's just, okay, we'll start by trial and error. 2 times 2 times 2. Will that give me 64? No. Certainly 3 won't do it. What can I multiply 3 times to get a 64? Is 4? Well, 4 times 4 times 4 give me 64.
16.
4 times 4 is 16 times another 4, 64. So the cube root of 64 on this one, we can actually simplify it and say 4. So the cube root of 64 is 4. Any questions on that? Now, the natural question to ask is, well, what if that top number isn't a 1? Like here on number 8. Notice there's not a, like if it had been a 1/4, you just write the little 4th root. Well, I have another rule to state right here. X to the m over n power. X to the m over n power. If you have some number up here that's other than 1, then, nope, you would flip it if you had a negative exponent, okay? The bottom number is always the root. This top number will be a power. So you actually have 2 things you've got to do here. Let me write it like this. If you have an m over n, you take the root and then raise it to that top power. X to the m over n. For instance, I'm going to make up one before we do number 9, because number 9 has some pretty big numbers. I'm going to use this. suppose we had 16 to the 3/2 power. I'm making up one with a smaller number than what we're going to see on number 9, just to make sure y'all see the pattern. And the natural question is, how does this differ from 7 and 8? 7 and 8, the top number was just a 1 in the fraction. So I'm trying to show you what you do if that top number is something other than a 1. There's one extra step. You start with the root. Take the square root of 16. Okay, I heard someone say that's a 4. And then raise it to that power. Okay? Take the square root and then raise it to the 3rd power. Did y'all hear what the square root of 16 is? Well, heck, even if you didn't hear it, you know it. The square root of 16 is 4. So we have a 4 cubed. Yeah, don't say 12. It's 4 times 4 times 4, which is 64. Now, sometimes students say, oh, I want to write this or punch this into a calculator. If you do, be very careful. If I punch in 16 raised to the 3/2 power, it is not going to give me a 64. What did I do wrong? If I wanted to punch this 16 to the 3/2 into a calculator, you've got to put the 3/2 in parentheses. Because do y'all remember that my dear Aunt, please excuse my dear Aunt Sally, the order of operations, it would do the exponent before it did the division. How did it get 2048? Well, it went 16 times 16 times 16. That got it 4,096, if I'm doing that right in my head. Then it divided by 2. That's not what you want it to do. You want it to treat that 3/2 all as one, as part of the exponent. Okay? Now, if you went 16 raised to the 3/2 power, then you get the right answer. Okay? Sometimes students say, oh, I want to use a calculator. Oh, this teacher don't let me use a calculator, whatever. Well, you sort of got to know how to use the calculator. The calculator isn't just going to give you those answers. You got to know how to punch the stuff in. So 64. Let me punch that in. Oh, wait, that's not the one that I did. Now let's do this one. Oh, wow. Now we're doing problem number 9. See, it has a lot bigger number.
That was just an example.
That was just an example. I'm sorry. Yeah, I said I was going to do an example with smaller numbers before we did number 9. I wasn't even listening to myself. 256 to the 3/4 power. 256 to the 3/4.
So then would there be the parentheses square root, but I'm sorry, I don't know what you would call it, but with the 4.
Yeah, just say 4th root. Just say 4th root of 256. And then once you figure that out, cube it. So let's see. 4th root of 256. What number could I multiply 4 on to get 256?
5?
I'm thinking if we multiply 5 5s, or 4 5s, we get 625. That's too big. So go smaller. What about multiplying 4 4s? Would that get me 256? What do y'all think? Yeah. So the 4th root, what am I going to put inside these parentheses? The 4th root of 256 is a 4. Oh, cubed. I have an idea of what that is.
64.
Yeah, 4 to the 3rd is 64. Same thing.
How?
Oh, that was just a coincidence there.
I'm like, all right.
Okay, so if in doubt, type 64 as your answer. That's a joke. Okay. It just so happens. Mm-hmm.
Question and stop.
Oh. No, oh, well, I'm glad you did. Let's see the next one. Oh, 9 to the 5/2 power. You know, I would like that. I think this would look more it looked nicer to me if the 5 were written, if the fraction was written sort of horizontally. Do y'all know what I mean by that? 9 to the 5/2. See, this might just be me, but I think it looks better. Rather than that vertical format for the fraction, which I was using right here. I used it, okay, but I thought it looks better with the 5/2 like that. Mm-hmm. So, okay, the square root of 9. So just what? Square root? Oh, this is problem 10?
I know what rule is that.
Oh, it's this one right up here. Mm-hmm.
Oh,
If the top number is anything other than a 1.
It's just differently written, so
Mm-hmm.
I'm confused with it.
Yeah, I should have written the 5/2 vertical, I guess. Okay. Let's see. So we're using that rule where if the top number is something other than a 1, the bottom number is the root, the top number is the power.
Yeah.
So we're taking, in words, we're going to take the square root of 9
And square it.
and then raise it to the 5th power.
There it is. 81 times 5 times.
Okay, so square root of, oh wait, square root, not square. What's the square root of 9? 3.
Oh, and then 3 to the 5th is
And the-
43.
3 to the 5th, if you multiply 3 out 5 times,
243.
you're going to get 243.
Where's that?
If I multiply 5 3s, 243. Oh, I think you went 9 squared, and that's where you had the 81. Am I right? Or did you say 81 a while ago? Or
Yeah, I did.
it would have gotten the numbers a lot bigger than this.
Yeah.
Yeah, I have no idea how you got it.
Wait, you have no idea? You said you have no idea how I got what?
No, I just don't know how you got the square root of 9. I don't know how you got the.
Oh, you know how I got. Oh, wait. I'm sorry. I messed up right here. Going from here to here.
So how?
You're taking the square root of 9. The bottom number is the root. And then should have done that.
I think
Oops,
that's where I
a
was
5.
confused.
5. That's a 5 right there. So you're taking the square root of 9. That gives you a 3. Then raise it to the top power, and that top power is a 5. So 3 to the 5th is 243.
Yeah, see now, okay.
Okay?
I'm following
Any questions
How
there?
are you going from square root
Oh,
of 9? Isn't that
yeah,
3
I had to
with
put
five?
that was my mistake. Parentheses and then the little 5. Let's see.
I know I need all the details.
Well, I mean, I've left out an
Once I
important
get it down,
detail
I'm like, I
there.
don't need it.
243.
First time writing
Number 11. Number 11 says, rewrite with rational exponents. It may be hard to imagine at this point, but there's a lot of times you would rather have something written with a fractional exponent than a square root. Okay? So, how would I write this? You're using these rules going backwards. These up here?
You can't see.
Oh, shoot. There. We are using these rules. We're going to go backwards. If you have a square root and you want to write it with a fractional exponent,
So would it be 23 with a 1 over 2 followed?
23 to the 1/2 or 1/2, whatever you want to call it, power. Okay? That's a key, that's a, how do I want to word this? Oh, why do I have all of this shown here? That's a very important rule that we're going to be seeing a lot of towards the end of this client lecture and on Monday when we're discussing logarithms. If you have a square root and you want to write it without that square root, make it a 1/2 fraction exponent. If you had a cube root, that's a 1/3 exponent. We're going to use this rule in reverse quite a bit over the next week. So the square root of 23 is the same thing as 23 to the 1/2 power.
Is that what it asked on the question?
Uh-huh.
Because I'm trying to
It says rewrite with rational exponents. So it's telling you to write it with fractional exponents.
So why couldn't you just use 3?
What do you mean?
Cube.
Because it's a square root, not a cube root.
It's not a cube root. It's just a square root.
Oh, okay.
Okay,
It
if
just clicked.
23,
Like if there was the 3 there, then it would be a 1.
Uh-huh.
There was a 3 over there.
you see, if you don't have an exponent, if you don't see a root here, you assume it's a little 2. Okay? But if there'd been a 3,
We can't see.
yeah. If there'd been a cube root, if there'd been a little cube there, then yeah, you would put the 3. Okay? But since there wasn't a number there as the root, we assume it's 2.
So that's going to tell you what your fraction is that number.
Yes. Uh-huh.
There's no number, it's cubed, and then you go down.
No, if there's no number, it's squared.
Squared. That is what I meant.
Oh, okay.
My tongue didn't wiggle right.
Oh, okay.
Did it wiggle right?
I see.
What sort of teacher has an ice pack in her
I've been doing the
office?
same thing.
She saw my swollen finger and sprang into action. Sandra.
Oh, wow.
Yeah.
So here, how would I write this one? It's still number 11. I just said similar question. 5 to the 1/2 power. A square root. Oh, Tim, I'll do this. There. 5 to the 1/2 is the same thing as square root. Let's see. What about number?
Oh, okay.
There it is.
Okay.
There it is for you. You knew what was coming ahead.
22.
Okay.
Exponent of 1/3.
What about those of you over in the peanut gallery? We're not hearing anything from y'all. Isn't it amazing the way the peanut gallery changed throughout the semester? Well, this used to be the peanut gallery. Now y'all are the peanut gallery.
I moved with you.
So, a cube root of 22.
Wait.
The cube root of 22 is, what's the fractional exponent I'll use? 1/3. So, cube root of 22 is the same thing as 22 to the 1/3. Okay, I got to tell y'all a little something before we do this one.
Okay, let me switch over.
Okay. But by the way, that's where we've ended the foundations part. We're about to start the college algebra part, so it's going to get a lot harder. I'm joking there. I'm joking. I never say when it's really hard. Okay. This semester we've seen things like quadratic functions and quadratic equations, something like x squared. That would be called quadratic. But up until today, we haven't seen anything where the exponent is where the variable is. Notice the difference between x squared and 2 to the x. If the exponent is, if the variable is up in the exponent, That's what's called an exponential function. Let me write an exponential function has the variable in the exponent. That's the first time this semester that we've seen variables in the exponent. Normally we have it the other way around. The variable is the base, and then the exponent is just a number, like x squared. Here it's reversed. The base is a number, the variable is, or the exponent is the variable, or the variable is in the exponent.
Make a note that the base can be any positive number except for 1. Why would you not have 1 to the x? 1 to any power is going to be what? 1 squared, 1 cubed, 1 to the 1/2. 1 to any power can be reduced. It's just 1. So the base has to be a positive number, but not 1. And when we start talking about the base of logarithms on Monday, it'll be the same restriction. It has to be a positive number, but not 1.
Or 0?
Not 0. 0 isn't positive, so it has to be greater than 0, but not 1.
So it can't be 1 or 0?
So it can't be 1, 0, or a negative number.
Yeah.
The base can't.
The base. Okay?
Assume the letter B is greater than 0. That means positive, and not the number 1. I'm going to show y'all how to graph f of x equals b to the x. The base is always positive. I'm thinking that was what we were about to do,
Yes,
right?
that's it. Now,
So I'm now telling y'all how to do something like problem 13 and 14.
we're going to do two things with exponentials today, two major things. Graphing them, and then we're going to solve exponential equations.
There's not a fancy name for an exponential graph, like with a parabola. Excuse me, with a quadratic function, the graph is called a parabola. Absolute value functions, the graph's a V-shaped figure. I guess we could call it a fancy name, a V-shaped figure. But for exponential functions, there's really no name for it. It's just a smooth curve. One end of it looks very flat. The other end gets very steep. So this end over here flat. This end very steep. It doesn't turn around or anything, just a smooth curve. It might be going up when you look from left to right, or it could go down when you look from left to right. Something like this. Oops. One end is very steep, the other end should be flat. That's the general shape of an exponential graph. I think this one looks better, doesn't it? Here, it looks like it's about to turn around or something.
Oh, I
It's
think
not
they
right.
both look good, Tony.
So,
Is that saying that it can never be in the negative?
if B
If it's
is
a positive number to any power, are you going to get a negative y value?
No, see, you're never going to have that little swoop.
it's never going to go down or turn around or anything. It could never have a negative y value, could it?
Positive number to any power, the y value is going to be positive. And the best way for y'all to see graphs, to be able to graph exponential functions, is just plot points.
Problem number 13. Well, actually, right off, this is multiple choice. For learning purposes, which of these graphs, there's only one that really looks like,
The general shape of an exponential.
you see? There's only one of them that looks like this. A looks like this one, okay? So if I had to guess on this, which I don't have to do, I would sure guess the answer's A.
But just plot some points.
Yeah, we're
And
going to plot
remember-
points.
Remember how negative exponents work. That's what we were doing those problems before we started this, making sure you know how these properties of exponents work. But my advice to you, to graph an exponential, plug in some numbers for x.
If you look at these graphs that you're given, it looks like it's going from 5 to -5 on the x-axis. I think as a general rule, if you just go from 2 to -2,
Okay, I agree.
that should be that's more than enough points. So there's no fancy way to graph an exponential function. You just plot numbers.
It's not like a parabola where you have your little
Minus b over
vertex
2a
formula that
and
you
stuff
use to
like that.
find the location of the vertex. No, just plot points and
So-
see.
And I think if you plug from 2 to -2 in, that's more than enough to get the shape. Be careful with these negative exponents and that zero exponent. I'm going to start off by plugging a positive 2 in here. I'd have 3 squared. 3 squared is 9. Okay. So there's our first ordered pair. We'll plot. I'll draw a graph in a moment and plot it. Now, plugging a 1 in for x, is that hard or easy? Yeah, 3 to the first power is just 3.
3 to the 0 power is
Don't say 0.
One.
Think back to the
Yeah.
first thing we did today. That very first
non-zero
rule.
to the 0 power.
Oh, right, it's 1.
Yeah,
One.
anything to the
Right.
0 power is 1. 3 to the 0 is 1. And now we're going to start with those negative exponents. So,
-3.
Be careful.
be careful. You weren't making that mistake earlier. If you had 3 to the -1 power, what did we say? If you have a number to a negative power, let's look back over here.
Oh, yeah.
3 to the negative.
So it's 1 over 3.
Okay, so it's 1 over. A negative exponent means 1 over 3 to the first. So that would just be a 1 over 3.
So for this ordered pair, you'll go left 1 and up a third. Just 1/3 of a unit up. What happens when you plug in -2? What are you going to get for y? 1 over 9.
3 to the -2. So remember that rule? We've done a lot today. That negative exponent was the second
right.
rule. So 1 over 3 squared. So 1 over 9.
But you square it, right?
The 3 squared?
Yes,
so
1
that-
over 3 squared. And then 3 squared is 9. Oh, let me see if I can.
Move it. Move it.
We never found our graph paper, did we? We lost our graph paper notebook. No. Okay, so right 2 up 9. 1, 2, 3, 4, 6, 7. Oh, shoot. Let's say right there is 9. So over 2 up 9. I suspect this is the very steep part of the graph. Then right 1 up 3. So we have this point, this point. The next point over 0 up 1. Left 1, up a third. Left 2 up 1 over 9.
Realize right here, if you broke from 0 to 1 into 9 little equal intervals, that's what 1/9 is. Or to the naked eye, it sort of looked like that point is just sitting on the x-axis, but it really isn't. There's always going to be a little gap between the gap between the graph and the x-axis. We say that the x-axis is a horizontal asymptote.
Which means it just runs beside it and never.
But it doesn't pass
So I just
through it.
extended a little
One
here.
side is very flat, almost horizontal. The other side, think about 3. If we had plugged in 3 for x, move your hand. At 3, we'd be way up here at 27.
Which would be
At
further
4,
than that.
3 to the 4th is 81. 3 to the 5th would be up there somewhere around the ceiling, 243 units up there. So realize it is extremely steep.
Mm-hmm.
Flat on one side, steep on the other. Is that what we said the graph would have to look like? Was that what response A looked like?
Let's see.
They're still drawing it, Tony.
Now see how I plotted the points. There's nothing fancy about it. Plug in 2 to negative 2, plot the points.
Okay. Let's
But
see.
you got to make sure that you're doing the 0 exponent right and the negative exponent right.
Response A. Yep.
Mm-hmm. And
Any
it could have been
questions?
B, C, or D. They don't even look like it.
They don't even look. They don't even look like those general shapes. Oh, we didn't mention that there's not an exponential graphing tool built into this course. Okay,
Yeah.
that's why the exponential graphs are done in terms of.
If I had to,
what's
yeah.
it called?
I used to think that Paul Pearson probably has some little programmer over in a sweatshop writing a code, but if they did, they would have already written an exponential graphing tool tool.
No,
Oh.
they do. It's my understanding practically all the programming for Pearson MyLab is done here in the
Yeah,
U.S.
we used to have a friend that was a
programmer for
Paul
Pearson.
and she got sick and they had to let her go.
Fortunately, her parents died and she inherited a lot of money, so, you know.
Oh, Tim, that's never an excuse to say fortunately.
No, it isn't. They were old and in poor health, okay? But
If you had to guess,
B.
B, you're thinking it's B because it's I'm thinking you're right that it's going to be B on this one. There's that negative exponent there. We said the base can't be negative, but the exponent sure can. It's definitely not going to be that one. That doesn't have the shape, and neither does that one. Okay? So let's see. Let's plot some points.
this is a good exercise in properties of exponents also.
This is probably number, which one was it?
14.
14. We're graphing y equals 2
to the negative.
to the negative x. I'll just draw my xy table, and I'm going to plug in from 2 to negative 2. Now, be careful because there's already a negative here on the exponent. So, are y'all caught up? Are y'all ready to start plugging the numbers in? We have the black 2 to the negative, and I'll put the 2 there. 2 to the negative 2. How will I simplify that? Oh, you've got the hang of it. Yes, 1/4. Did y'all hear that? The negative exponent is a 1 over. So 1 over 2 squared, 1/4. So I think this side is going to be the side that has the flat part. Now, 2 to the negative 1. A negative exponent means 1 over. Yeah, just a half. 1 over 2 to the first. 2 to the first is just a 2, so 1/2.
Yeah.
So over 2 up a 4th, over 1 up a half.
Plugging in zeros easy. 2 to the 0 is 1. That's right. That
2 to the
definition
0 is 1.
Exponent.
Okay. Now when we plug in a negative 1 and a negative 2, are we going to have any negative exponents? No. You see it's going to be 2 to the negative, so positive 1. 2 to the positive 1 is 2. If I plug a negative 2 in here for x, negative 2 will be positive 2. So 2 to the positive 2, what's going to go right here? Do y'all see how I found those numbers? Any questions there? Let me draw my graph.
Just doing the same steps, right?
Oh, yeah. The only difference is the numbers are slightly smaller because the base was a 2 rather than a 3. Oh, right here? Okay. So if we plug a negative 2 in here for x, we're going to have 2 to the negative. No, negative. There's already one negative. If you put a negative 2 here, negative, so it's a positive 2. Let me write it like that. 2 to the positive 2, which is 4.
That's where I got lost. Okay.
Any questions? So we start off over 2, up a 4th. That's not up very much, is it?
So it looks like the right side's the side that's going to be close to the x-axis.
Over 1, up a half. Yeah, you're right, Tim. Over 0, up 1. Left 1, up 2. Left 2, up 4. 1, 2, 3, 4. Connect the dots.
That's right. It's not as steep.
Just draw this out a little bit and put an arrow. And same thing here, going up. Any questions there?
And I agree. This box B.
Okay, based on this, so not to try to do a cheat program. Based on this, if you have a negative, you're going to be going to the left. If you have a positive, you're going to be going to the right.
Let me see.
So you could. Does that make
Show
sense?
it.
What I'm trying to-
If you have just y equal,
Move it up.
if we're comparing between a positive x here and a negative x.
Yeah.
If it's a positive x, it's going to go up like this, and that's what you're saying.
Yes.
If this had been negative, it's going to go down like that.
Provided the base is greater than 1.
Yeah, of course, the base has to
You'll
be.
never have
Well, if it were,
anything under the X.
it shouldn't, because the base will always be positive. There's no reason you would ever. There's no way to have a positive number raised to any power and get a negative number.
A positive number to any power is always positive.
And you
But-
might say, well, wait a minute, what if the exponent is negative? That don't matter. If the exponent is negative, that doesn't mean you get a negative answer.
Right.
It means you get a fraction as your answer.
Right.
Okay? And so, here, let me do this.
Now the
Always above. Oh, I was just saying, there's the... I'm trying to... it looks like it went across it, but it's not supposed to. Okay? It does not cross the x-axis. Let's make a note. Someone says, say something about graphs of exponential functions. You can say, exponential functions do not cross or touch the x-axis. In fact, they're always what? Above or below the x-axis? Which one? Above.
Sorry.
Okay?
Oh,
They are always above the x-axis. Oh, sorry. So,
I need to try to use it, so I'll take over now.
oh,
Now we'll solve some exponential equations. You better give me that microphone.
oh, okay.
I'm taking off the ice pack. I think it was getting a little frostbite. So, oh goodness. Oh, don't ask.
I'm not even sure exactly what happened. But anyway,
Okay, exponential equations.
what we're about to, wait, let me show something. Where's the little thing, cursor?
Okay, I can't do it.
Okay.
Okay. As soon as I start putting pressure on it.
Okay, I'm now going to show y'all what we're about to do, and this is for the rest of the assignment. We're going to be solving equations. This is the first time this semester we've had an equation where the variable is in the exponent. So it's sort of important to be able to distinguish. How does this differ from those when we were solving using the quadratic formula? Well, in the quadratic formula, the equations were x squared. The variable wasn't in the exponent. Number 15 is not the first one we're going to do, but
You'll notice all of these equations have the
variable in the exponent. Okay? So here's what we're going to do. To solve,
Well, actually, to solve exponential equations, there's two methods, two generally accepted methods. The same base method or a logarithm method. Well, we haven't discussed logarithms yet, so the only method you're going to have is what's called the same base method. And if you think about the same base method, it'll make sense to you. It should make sense.
to solve an exponential equation, that's an equation that has the variable in the exponent, try to write both sides with a common base. And I think that y'all could all solve this first one just by inspection. 3 to the x equals 9. Could y'all figure out what number x is?
What exponent do you have to put on 3 to give, what
what
exponent you put on 3
exponent?
will give you 9.
3 to
Okay.
squared. 3 squared is 9. Okay? So if you were solving 3 to the x equals 9, you could say, okay, x is 2. And what was that intermediate step that I'm not showing here? Well, you took the 9 and you thought of 9 as 3 squared. Think of 9 as 3 squared, and then, okay, if the bases are the same, the only way these can be equal would be if the exponents were equal.
If the bases are equal, you can drop the base, set the powers equal.
Could we do that on this problem? 3 to the x equals 7. Could I write both sides with a base of 3? Yeah, that 7, you cannot write it as 3 to a power.
That's the drawback to the common base method. You have to be able to get the common base on both sides. And if it's impossible to get the same base on both sides, you'll have to use logarithms. And I think we'll see that 1 week from today.
I'll say use logarithms next week. Okay? for today's assignment, we'll be able to get that common base. Okay? Let's do, okay, problem number 15. 16 to the x equals 4. What's 4? Let me switch over. Okay, so you're thinking that 16 is, we got it the same base on both sides.
Yeah, I'm very
So it'd be
confused.
4 squared.
Okay, start with a bigger number and ask if you can rewrite it with a smaller number. That's what we did here, isn't it? We rewrote 9 as 3 squared. So, well, you already got the answer. What I would do is this. Rewrite the 16 as 4 squared. I'm taking the bigger number, rewriting it as a power of the smaller base. So rewrite 16 as 4 squared.
What power do we have on this 4 here on the right?
If there's not an exponent showing, what power do you assume is there? Oh, wait, 1. Right here. There's a 1 on the right. Now, you know what? I'm about to assume
There's something called the power rule of exponents, and I'm not sure that,
I don't think we should assume they remember it. So
Yeah,
let's state it.
if you have a power raised to a power, what can you do to rewrite that as a single power of the base?
You multiply. If you have one power raised to another power, you multiply those together. Generally in algebra, whenever you have parentheses, to get rid of them, it's going to involve some sort of multiplying. So like right here where I rewrote the 16 as 4 squared, 4 squared to the x, we would write that as just 4 to the 2x equals 4 to the first.
This power rule of exponents is important, and we'll be using it quite a bit. Power raised to a power, you multiply to write it as a single exponent. 2 times x became 2x. Once you get the same base, you can do what we did here. Once you have the same base on both sides, drop the bases, set the exponents equal.
Since the bases are the same, the only way these can be equal is if the exponents are the same. So dropping those big 4's, we have 2x equals 1. Is that an equation we know how to solve? Divide by 2, yeah. So we have x equals 1/2.
The work in the problem will be to get the same base on both sides. You want number to a power equals the same number to a power. You don't want any parentheses, okay? Just number to power equals same number to power. You drop them and set the exponents equal. That's going to be the work. Sometimes you may have to change both sides. Okay, so
Figure out the common base. But for every one of these problems, there's a common base. If there weren't a common base, then we would have to be doing something with logarithms, which we're not ready to do yet. But it's a good question to ask. Well, what if there isn't a common base? You'll be able to answer that in 1 week's time. Let's see.
no,
Wednesday. Okay. But number 16. This is a better one than number 15, I think. 3 raised to the 2x minus 7 power equals 81.
Switch into paper.
Ooh, this has got to move out.
Generally, I take the small number, the small base, and I ask myself, can I write the big base as a power of the small base? What do y'all think? Okay, I agree.
Okay. Did y'all
3
hear
to
that?
what power will give us an 81? 3 to the 4th power.
So we rewrote 81 as 3 to the 4th. Now, how did I get that?
So fast.
Oh, how did you get that so fast? She thought 9 times 9 is 81, and 9 is 3 times 3. I don't know. How did you get that so fast? Okay, let's take a look. Okay. Normally, if someone had it immediately said it, I would have said, okay, let's start multiplying 3s. How many 3s would it take? 3 times 3 is 9, times a third 3 is 27, times a fourth 3 is 81. So 3 to the 4th is like 9 times 9, so 81.
Okay, and then now you're going to do 2x minus 7 equals 3 or 4.
That's correct.
And then
Once you have the
bring
same
her out.
base on both sides, drop the base, set the exponents equal.
So we're solving 2x minus 7 equals 4. And how would I go about getting that x by itself now? Okay, add 7 to both sides. Very good.
X equals 11 over 2.
Uh-huh. Then divide by 2. Did y'all hear 11 over 2? There it is. 11 over 2.
The trick is getting the same base
Base.
on both sides.
Mm-hmm.
So, any questions there before I type in the answer? She's still writing.
Oh, okay.
Yeah, I'm just confused, so I'm just trying to
Oh,
understand
no.
it as I'm writing.
Oh.
Once you get the matching bases, forget about them.
I just don't understand how you got 3 out of 4 power so fast. It takes me like 10, 20, 30 minutes to find that, so I don't know how
You have
you
your
did all
calculator
that.
there.
Start multiplying 3s
Well, I
together.
know 9 times 9
Uh-huh.
is 81.
Here's
but I don't know
something
how
to
you're
think
getting-
about.
3s.
3 is a prime number. 3 is prime. You're not going to change 3. You're not going to change the 3. It has to stay a 3, okay? And so you've got to be able to use a 3 to write 81 if you're going to get a common base.
And how do you figure out 4? You just start multiplying 3s together. Okay, how many 3s does it take?
I would be like sitting there trying to
Well,
figure
3
out
times 3 is 9, times a third 3 is 27, times a fourth 3 is 81. But it has to have a common power, a common base. Okay?
Forget about the 3s.
Once you have both sides with the same base, you're through with the big 3s. If the bases are equal, the exponents have to be equal. Okay? And number 17, since students
17.
usually have trouble with number 16, number 17 is very similar. Let's see, number 17.
Maybe this one would have been a better problem than number 16
Yeah.
to do.
3 to the 2x minus 5, oh yeah, equals 9. Yeah, number 17 would have been a better one than 16. Do 17, then 16.
Are the rest of these like just the exact same as this?
No.
No.
We still have another type of, we need to introduce a new irrational number, but
Not
it's still
new.
the same type of,
All common base.
it's all common base problems.
But they're going to be common bases with square roots in them and other stuff.
Okay.
Okay.
Like the 9 is 3 squared.
Like the 9 is 3 squared. Did you write 3 cubed? Yeah, that's common. That's a common mistake. 3 times, you're thinking 3 times 3 is 9, and you put 3 as the exponent. No.
And then we drop the bases, setting the exponents equal.
So, you see, if you can do 17, then you can do number 16. 16 just took a little more thought figuring out how many 3s.
Well, no, it just made
Okay,
You
so
said
two.
that they have some
702.
math. Now it's a lot easier for me to understand.
Okay.
7/2.
I thought there was like a billion different numbers that I could.
7/2.
7/2?
Why do I have
Hmm?
7?
Any questions with how I solve that? Isolate the x by adding 5 to both sides. So we have 2x equals 7. And then divide both sides by 2. Get x equals 7/2. 2. Oh, I want to wait on. Well,
no, I'm gonna do
let's
it.
right. Let me
Okay.
try it again. I got to try
Are
to
you going
write
to
with
define
this
what
hand.
an irrational number
I sure
is?
am.
Okay, here.
What kind of E is that? Is that an E?
That is an E, and it is not a variable. It's a number.
It is a number.
Well, Tim will tell you.
It's calling
And-
itself a number.
An irrational number, we've talked about rational numbers, we found rational zeros. A rational number is any number that can be written as a fraction, one integer over another integer. An irrational number can't be written as integer over integer. An example, I'll say it's a non-repeating.
We can't see.
Oh, no. Uh-oh. I fell down on my job. Thank you.
Okay. An irrational number is a non-repeating, non-terminating decimal number. So it never repeats the same block of digits. The digits just keep appearing randomly, basically. And it never ends. A non-repeating, non-terminating decimal. And since the digits never end, to express the exact value, you have to use some sort of symbol. There's a famous irrational number, probably the most famous irrational number that there is. It's defined as the ratio of the circumference of a circle divided by its diameter. Take the circumference, divide it by its diameter, and that gives us 3.14159. What is that? Pi. That's an example of an irrational number. You have to use a symbol to represent the exact value because the digits never end. Well, we've been working with irrational numbers since the first day of the semester. It turns out any square root that's not a perfect square is an irrational number. The square root of 2. Those digits never end. The square root of 3. What about the square root of 4? Is the square root of 4 irrational? No, that reduces to 2. But the square root of 5, and so forth. Well, there's another irrational number that has important applications in business and scientific problems. It's called the natural exponential. The natural exponential we denote the natural exponential using a lowercase letter e, and the approximation, just like pi is approximately 3.14, the approximation for e is 2.718.
Why the squiggly on
It's just that's saying approximately equal, okay? The little squiggly lines is an equal, but it's saying I'm rounding the number, or I'm stopping the digits there. So it's an approximation. The approximation doesn't really matter for our point. From our point of view, we're going to be using the exact value for e. The thing to remember, e is an irrational number, and e cannot be written as a power of anything other than e. So when we look at that number, that problem that was just showing up there, that equation, for a moment it looked terrible. There it is. This is number 18. Let me write it down. E
to the 8x minus 1 is equal to e to the 6th all raised to the x power. Know someone that broke their ankle recently, just like I broke mine in May, and this person was like, oh, I was like, well, you got to stay off your ankle. Oh no, he's walking on it, he's got to work through the pain. No, this isn't a pulled muscle or anything, this is a broken bone, and I'm wondering, am I doing the same thing with my middle finger now? Okay, do you think I broke something in it? But I can bend it.
You need to buddy tape it.
I need to what?
Buddy tape it.
Buddy tape it?
And you can have it look at.
Oh, okay. What does that mean?
So tape one finger next to it, which is
Uh-huh.
the one you don't want to
Uh-huh.
use. I would do it with this one because you could still write like this.
Uh-huh.
And then you put like 2 or 3 pieces of tape.
Oh, the surgical
Around it.
tape. I had plenty of surgical tape.
You can
Okay.
use surgical until you can go have an x-ray, and then they'll still do the same thing if you have an x-ray.
Oh, okay.
But I'm not
I'm
giving you
gonna
medical
buddy
advice.
tape this, okay? I'm gonna buddy tape my hurt finger.
That was not medical advice though.
It was not. I know it wasn't. Okay. One thing that's nice about E is an irrational number. If you're going to use the same base method, you have to have an E on both sides. And yes, we do. So all we need is just e to the power equals e to the power. Well, what are we going to do here to get rid of these parentheses? E to the power raised to the power, what's that going to become?
6x.
Okay. You multiply 6 times x. And then what can I do?
8x minus 4 equals 6x.
So you have the same base on both sides, no parentheses. You drop the base, set the exponents equal. Now what do you want to do?
Minus 6x.
Okay, I like that. Well, minus the 6x. 8x minus 6x is going to give me 2x, okay. What are we going to do with that minus 1? We have a 2x over here on the left side. I couldn't hear you. Okay. I agree. Move the minus 1 over. That became a positive 1. So we have 2x equals 1. Divide by 2 to give us x equals 1/2. Okay. Let's punch in. One half. Any questions there?
If there is, I think there's another one similar to it. Right here.
Okay. Make sure you got the hang of this E stuff. Number 19, let me write it down. E to the 12x minus 1 is equal to e to the 10th, all raised to the x power. I'm going to let y'all tell me what to do, okay? Okay, so power to raised to power you multiply.
Minus 10.
Okay, and so we then drop the e's, set the exponents equal.
The same thing.
You know, I think I may be writing neater. What do y'all think?
I think you are.
I think I am. So maybe I should break my fingers more often?
I don't think that's the solution.
Okay, what did you say? You said minus 10. That's going to give me
The 2x.
another 2x. Oh, look at this answer.
Yeah.
Oh, wow.
And then
A positive 1.
to give us x equals 1/2.
If in doubt, guess a half.
Guess a half. If
That's
you're,
it. I'm joking about that.
okay.
I'm gonna use
It
it now.
just so happened, it just worked out like that. What was it, 64 earlier? It turned out
64, I must have missed that,
You gave an
okay.
example,
And
and
the
you got
answer.
64, and then the actual problem equals 64.
Oh, so we now know. If in doubt, guess either 64 or 1/2.
These E problems look terrible, but they're actually easier
And
because you know
realize-
the base.
And E is not a variable. E is representing a number.
2.71828182846.
And all you have to actually do
Four,
without even
six,
doing
five, two,
anything
nine.
is just take the 12x minus 1 and then equals 10x.
Right.
You don't even have to look at the e's.
Yes, you don't.
That's why I said the exact value, the 2.718 blah blah for E doesn't really matter.
And I told
Okay.
Tim before class, I said, should we skip that step? Oh wait, y'all don't see what I've covered over.
And I said, oh no, Tony, we're going to show
Wait,
this step.
Look, put the pen back there to show. So you could go from here to right there, 12x minus 1 equals 10x. I bet a lot of people eventually will start doing that. Rather than
Okay.
writing that extra step with the 10x.
Number 20.
Number
this
20
is
is
a-
a doozy.
Don't tell me that. I do not want
No.
16 to the 3x minus 3 is equal to 64 to the x plus 3.
You probably never thought you'd see the day. You'd think, oh wow, I wish that was the irrational number E there instead of 16 and 64.
There's also no prints.
There are no parentheses, not yet, but
As a general rule, I ask myself, if there's no common base, can I write the big number using the small base?
well,
If I-
16 to the first is 16. Write that out just to verify.
Oh,
16 to the first is 16.
Yes.
And y'all are saying 16 to the fourth? Okay, right. Let's see. Is that 64?
Is 16 to the fourth 64?
Oh,
No.
16 times 16 is
16 times 1.
16 times 16. Isn't 16 times 16 256? Punch that in. What's 16 squared? I'm thinking it's 256.
Yeah.
So I don't think there's going to be a way to write 64 with a base of 16.
Do y'all see the problem or the difficulty? What's wrong here? We cannot write 64 as a power of 16.
Put a product in trial. Write 16 here and then a question mark.
16 to what power? 16 to the first is 16. 16 squared is 256. You can't, you're going to have to change both sides.
16 will divide into 64 4 times.
But that doesn't, that 16 to what power? You're not dividing. You're saying 16 to what power gives you 64? 16 to the first power is 16. 16 squared is 256.
You're already too big.
I'm already too big. It's something between 1 and 2, but we don't know what. So we're going to have to change both sides.
Look at this one.
Oh, that was that's good.
Okay, look at the small number 16. There's a certain fact from the multiplication tables that involves 16. A number to a power is 16.
I think you can change both 16 and 64. How do you write 16 using an exponent? Well, so you're thinking 4 squared. That's what you're thinking? Let's try that. 16 is 4 squared.
Why did you decide on that? Well, again, these are rigged to work out. If you're thinking, well, wait a minute, what if that 16 was a 15? No.
You got to be able to get a common base. Now, let's write 64 as 4 to the power. 4 to the third power, 4 cubed. Good.
This is one of those that takes a lot of thought. Okay.
Was that a
So what happens if you've got to change both bases? You might have to change both bases. So start with the smaller one, change it so it's written as an exponent, and then try to write the bigger one using that same base. 4 squared is 16. 4 cubed is 64. And did you show that on a calculator for the people that didn't believe it?
So then when you
4.
get rid,
If I multiply out 3 4s, we get 64. And now what did you say we do?
you get rid of those now?
Well, we got to get rid of the parentheses. We have a power raised to a power, so what are we going to do?
Just multiply.
Okay, good.
You're going to multiply and I heard distribute.
6x
Okay, we're multiplying the 2 by the 3x minus 3
minus 6.
minus 6. I agree. We're distributing the 2 over the 3x minus 3. What are we going to have here?
3x.
3x plus 9. Good.
And then you get rid of the 4.
And then, once you get to this point, it looks a lot better. You drop the 4. Remember I said the major work will be getting a common base. And this problem illustrates that. You have that common base, drop the 4, set the exponents equal. What do you think I'll do to solve this?
Subtract 3 and add 6.
Okay, I agree. Subtract 3 and add 6. So that's going to give us 6x minus 3x. That's 3x equals
15.
9 plus 6. I agree with 15. And then divide by 3 to give us x equals, what did he say?
5.
I agree. Any questions?
Again, they're rigged to work out like this. If you're thinking, wait a minute, if that 16 were 15, how would we do it?
You cannot. It requires logarithms.
Mhm.
You've got to be able to get a common base.
Here's the question.
Yes.
Why wouldn't you put like a logarithm with this lesson?
Well, you could solve this one with a logarithm.
But it takes a lot of logarithmic discussion and properties to get to the point where you can solve this. So we're going to work with
Theoretically, you could do
logarithms.
this one with logarithms.
Oh yeah.
It just, this common base is the easier method.
Yeah, I was going to say, what is the easy one?
Common base. Okay.
So this is called
If
the
you can
common
use a common base, yes, this is the common base method. When we start the next section where we're solving equations, I'll say, okay, to solve logarithmic equations, there's 2 methods. The common base method, we saw that on Wednesday, April 5th, and then this new method with logarithms that we'll see in 1 week's time. Did you punch in 5, Tony?
Not yet. Oh,
Okay,
yeah, I
yeah,
did.
I
I
Okay.
thought maybe, I don't think 21 is exactly.
Okay. Well, let's see it. Let's see if you do a similar
I
problem.
think I'm going to do a similar. Okay, back
Oh.
to E for 21. Let's do similar question on number 20.
Oh, I
This
think
is-
21's
Oh,
not.
shoot. No, it's the same problem. Or basically the same. Don't write that.
Click help me solve it here.
No,
And then,
next up, no,
oh,
Okay,
there's a
here's
good one.
Okay, so this is another number 20. Because there's only one like this in the assignment.
Okay. Let's switch
My
over.
first thoughts are always, can I write the big number, 729, is a power of the small one, 81.
Let's see. 81 to the first is 81. We know that. What about 81 squared? Is that going to give me 7?
761.
I think we've gone too big.
You punch that in your calculator, right?
Yeah.
Oh, okay. I was wondering if you'd done it in
Yeah,
your
that would be intense.
Okay,
I did that
so
too.
go to the small base, write 81 using exponents. There's something that stands out to me. If I were going to try to write 81 using exponents, how could I do that? 9 squared. Okay. What about 729? Play around on your calculator.
How many 9? 9 times 9 is 81. If I multiply by a third 9, am I going to get 729? Yes.
So 9, you can use 9 as your common base.
Y'all see how we chose that?
81 is 9 squared. 729 is 9 cubed.
This is some nice number theory. Again, it's logical to say it's rigged to work out like that. Yes, it is.
And then you just drop your 9s and work your exponents.
Well, let's see. First of all, let's get rid of. I'm going to get rid of those parentheses by doing what?
Yeah.
You were working ahead of me, weren't you? So what am I going to do here? Power raised to power, so we.
6x.
Okay, so we're multiplying 6x minus 12. I agree. So distribute. Here, 3x, keep going.
Plus 12.
I agree. You distributed the 3.
Will we write the red 9s anymore?
No, the red 9s are gone. So you just set the exponents equal. And what do you think I'll do? Minus the 3x and add the 12. I agree. So 6x minus 3x gives me 3x. 12 plus 12 is, and then to give us, okay, good.
That's another number 20. So you'll sort of get the hang of, sometimes you've got to change both bases.
Okay. Punching the answer 8.
All this
That stuff is
it's leaking out of your ice pack.
I
That
know.
gel. What's the answer?
8.
Yes.
Yes.
Okay.
Now.
Now.
Tell Sandra I busted her ice pack, okay?
Okay. Now.
Okay, number 21. Hold on.
Put a 1 over it.
I'll see it.
Number 21. Oh, number 21 looks terrible.
Is it terrible?
But
No,
it
no,
really is
no,
that
no,
because
no.
what's the common base going to be? Okay, I
If
was going to
the-
give a hint. It started with E. If there's an E in the problem, that's the common base.
If there's an E in the problem and you're going to get a common base, it must be an E. X plus 8.
This works so much better now with all those first problems rather than just
Jumping in college algebra.
jumping in college
And the
algebra.
standalone college algebra course where, okay, y'all remember those properties of exponents, right?
Let's go.
Where's the cursor? Oh, there it is.
Yeah. That's what they don't with that.
Yeah.
Okay. We know we want E to be the common base.
Why don't you write E there?
You want E to be the common base because you can't write E as a power of anything other than E. So we want E as a common base. And here's another thing. I generally avoid bases that are fractions. You say, well, I'm going to use 1 over E.
Oh, don't.
That's it. No. Do not use a base that's a fraction.
So we're going to go back to something we were doing
Where is it?
right out here on number 5 and 6. Look, number 6 is a good one. We had 1 over P to the 6th. What did we do to write it without the 1 over? You make the exponent negative.
You say, well, I don't even You're saying, I don't even see a power here on this e, so what do you assume the power is? Okay, a positive 1. So to get rid of the 1 over, you make the exponent negative, so you have an e to the negative 1. Agree with my logic there? Now, I'm not going to say anything. What are we going to do to rewrite 1 over e to the 6th just as e to the power? Negative 6, I agree. Any questions there?
Now it's very similar to the E problems y'all did earlier, but
And then it would be a positive x?
That's right. But let's go back before we go any further. Any questions? The trick in this problem here, the work, is to realize you can rewrite both sides just as a power of e.
that red 1 over is the same thing as that red negative. The red 1 over is that negative on the 6th. Well, I just made it look messier. Well, it looks black now.
No, I can tell that I can tell that you tried to make it red. That was a good idea. So power raised to power, Mary May was saying.
Positive x.
So you multiply negative 1 times negative x is a positive x. Here,
Negative 6x.
keep going.
And negative.
No.
Yes,
Yes.
it's negative.
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 48, I agree. You took the negative 6 times x, that gave us the negative 6x. You took the negative 6 times a positive 8, that gave us that negative 48. And now what can we do once you have the same base on both sides and no no parentheses? Drop the base, set the exponents equal. So you have x equals negative 6x minus 48. What do y'all think I'll do? I'd plus the 6x,
So you get a 7x.
1x plus 6x, I agree, that's a 7x,
So you get 8 7.
equals negative 48, and then you divide by 7, and you get negative 48 sevenths, I agree. Any questions there?
If there's an E in the equation, E should be the common base.
There's an e in the equation. It's going to be
Well,
ish.
okay.
Well, if there's an E on each side.
It has
How
to
is that?
Yeah.
Now, suppose we had an E on one side and no E on the other side. Then you could not get a common base. That's when you're going to use logarithms. We'll see that next week. Did you punch in the
No,
answer?
it's gone. Okay. Negative 48 over 7.
There's one more or two more?
2 more.
I have another.
They're the last two, so they've got to be the hardest two.
Right.
Wait, what was the 48?
Oh, wasn't it?
Negative 48 over 7.
But
Negative 6 times x is negative 6x. Negative 6 times 8 is negative 48.
Stupid.
Yeah, 'cause more than
I put 8.
Oh, you didn't distribute. Oh,
Yeah, I'm trying to catch what
okay.
oh no.
Any questions,
I
y'all?
did it in my head. I just didn't write it down.
Oh, well,
Negative 6 times x is negative 6x. Negative 6 times 8 gave me a negative 48. So we have a negative 6x minus 48.
I did it in my head and I didn't write it down.
Oh, well, be careful. Number 22.
22 and 23, I was trying to hint at what was common
No,
earlier. When,
they're not
Show
that
us.
bad.
oh, I know.
Let's see. Wait a minute. Remember, where's those radical
I know,
problems?
right? Keep turning.
Right here.
Right here. Oh, let me see.
Remember,
in particular, this one and this one.
let's see.
I think that's when you were coming in.
Mhm. Remember, a square root is the same thing as an exponent of 1/2. A cube root is the same thing as an exponent of 1/3. Okay? Let's look at number 22.
Don't panic when you see it.
You're preparing us.
Okay, that's not bad. That's not bad.
Okay.
Square root of 2 raised to the x plus 1 power equals 16 to the x. Here's something you're going to want to remember. You're going to add this to your bag of tricks. As you work through the exponential and the upcoming logarithm assignments, if you see a radical, you're going to want to rewrite it using an exponent. And that'll be true not just in this assignment. When we're expanding and condensing logarithms next time, when we run into radicals, we're going to have to write it using an exponent. So add this to your bag of tricks. I see a square root of 2. I'm going to write that as 2 to what power? Oh, Tim. Oh, oops. Okay. How do we rewrite a square root of 2 as 2 to a power? 1/2. And that's what we did right back over here, like 5 pages. Yeah. There it is. The square root of 23 we wrote as 23 to the 1/2. If it had been a cube root, you would have written a 1/3. The square root of, add it to your bag of tricks. When you run into radicals, you're going to have to write it using an exponent. So we have a base of 2 on the left side. 2 is our base. 2 is a prime number. You're not going to change 2. So you better be able to write 16 as 2 to a power. Don't say 8. How many 2's do you have to multiply together to get 16? Is it 4? 2 times 2 would be 4. Times 2 is 8. Times 1 more 2, that's up 4 times 4. 2 to the 4th is 16. And if you're using a calculator like this one here and you want to play with, just use the exponent button. 2, you see the little upside down V, that's called a caret top. 2 to the 4th, sure enough, that gives us 16. So we write 16 as 2 to the power 4. You have to have the bases be the same, and you can't have exponents. We have powers raised to powers. What are you going to do? My way or your way? I'm gonna say power raised to power. What do we do? You multiply, so 1/2 times x is 1/2 x plus 1/2 times 1 is 1/2. Is that your way? And then power raised to power
is 4. And you get rid of the 2.
Okay, then we can drop the bases. Any questions? Any questions? Any questions over there in the peanut gallery? No? Y'all are following? We drop the 2. We set the exponents equal 1/2 x plus 1/2 is equal to 4x. Well, I just look at the denominator. The only denominator that appears is 2 multiplied through by 2. You have to how many terms do we have total? How many times are you going to have to multiply by 2? 3. You're going to have to multiply here by 2. Here by 2, I'll put it right there. I think there's more room. Maybe it'll look better if I put it as 2 over 1. And here by 2. I think that's what you were saying about this. Yes. Mm-hmm. I think that's what you were saying when you about the reciprocals. Mm-hmm. Yeah. Mm-hmm. And that cancels very nicely. What are we going to have here?
X plus 1.
Okay, so wait. X plus... The 2's cancel, so x plus 1 is equal to 4x times 2. I agree with 8x. Subtract the x. So you have 7x equals 1. And divide by 7. I agree. To get x equals 1/7. Okay. 1/7.
Any questions? Put it back on my work
The
here.
key is rewriting the square root with the 1/2 exponent.
That is the key. And add that to your bag of tricks. It's going to keep appearing in the next assignment, okay? A square root or a cube root or whatever sort of radical. You're going to have to write it using an exponent. A rational exponent, a fractional exponent.
Now let's see about the last one. Oh, wow. Finally going to be through. Oh,
It's the same, isn't it?
oh, it's very, very similar.
See about view an example. Don't write that
No,
one down.
let's
Let's
see
see
if
if
we
we can, help me solve it. Let's see if I can get, let's
Let's
use
do
this
this
one. I like this one better. 23. We have a square root of 3 raised to the x plus 5 power is equal to 81 to the x power.
How did we get this done in an hour and 35 minutes last fall?
I don't know. I really don't. I wonder if we did all the problems.
Yep, we did.
Okay. I see a square root and I know I have that trick. I'll rewrite that square root as 3 to the.
Or you might want to 3 to the 4th.
Okay, you're getting ahead of me. This one I'm going to write 3 as. The square root, 3 to the 1 over 2. And then over here, 81 we can write as you said 3 to the 4. Okay. And powers raised to power, so we multiply the 1/2 times the x plus 5. That's going to give me a here
And 5/2. I mean, a 1/2 x.
1/2 x
5/2.
plus 5 over 2, I agree, equals 3 to the 4 times x is 4x. And then drop the bases, set the exponents equal, so we're going to have 1/2 x.
And then
Okay, so I'll write in red. 1/2 x plus 5 over 2 is equal to 4x. And what did y'all say do?
multiply by 2.
Multiply by 2. I agree. Twos cancel there to give me here.
X plus 5 equals 8.
Okay. Any questions on our logic up to this point? Okay, so you subtract another, this is like this one up here, isn't it? We subtract the x above and below to give me, above and below, from both sides, subtract x from both sides to give me 7x equals 5, and then divide by 7 to give me 5/7 for my final answer.
Anybody? 5 over 7. You can show both of those on the same page. They look I'm sure.
Yeah, there looks. Yeah, let me show you. It's called a manual zoom. Sometimes you just got to do a manual zoom. There. Almost.
They're 22 and 23 are sort of similar, aren't they?
Pretty similar.
I'm pretty
Yeah.
sure they're the exact same.
One's 81 and
Yeah.
one's 16 and
Oh.
one's 30 and one's 2. There's no
Yeah.
difference, but there's problems.
Any questions?
But it's the same like formula.
Oh,
I'll tell you right now.